maybe I should start with telling you a bit about some categories of let's say, operator theoretical category. So there are sister algebras. I'm going to explain in 2 minutes what sister algebras are, and we're going to dive deeply into this part. And there are special kinds of sister algebras called von Neumann algebras. And there are also so-called operator systems and operator algebras. Every sister algebra is both an operator algebra and an operator system. And there is something that sits here, which is called Euclidean operator space. And the title of the course is Topics in Operator Algebras, meaning that at some point we probably have to discuss about these guys, right? But in fact, you can talk about operator algebras without knowing sister algebras and also operator systems. So all of these three are going to be main ingredients of our course. Let's say at least half of the course is going to be the theory of sister algebras and operator algebras and operator systems. And here and there, maybe I will say a few things about von Neumann algebras or about operator spaces. But this is not a course about von Neumann algebras, and this is not a course about spaces. Okay, so we are here in the middle of this course. And yes, and in the second or the third part, depending on how you count. So I said this will be the first part, these guys will be the second part maybe, and then the third part will be applications to dynamics, to group theory, etc. But by the way, we can change it a little bit. I mean, if you have some special interest, you can ask me and maybe we can be more flexible. But yes, but as of today, we're going to start with system. So people at home, can you read everything I write, or is it too small? It's okay, great. Awesome. So let's start. Let's start with some definition. Definition. By the way, before that, do you have any question about the course, about this? Anything that has to do with it? Anything that's technical? No. So definition, a Banach algebra is a Banach space. Of course, and which is also a complex algebra, complex meaning over the complex numbers, such that there's a connection between the multiplication and the norm, which is the norm of AB is less than the norm of A time. Some examples. So if X is a Banach space, then I can always consider the bounded linear operator over it, or continuous linear operator over it, U of X, with the operator norm. So what is the operator norm? Just to remind you. It's supremum over all vectors uniform apply them. Yeah? And so this would be, let's say, example 1. Example 2. And this X is a compact out of space. Then we can always consider the algebra of continuous functions over X with the supreme maximum, right? Feel free to interrupt me at any point and to ask questions. Also enable you can ask questions. Yes, and in fact, we can take an example to a step further and to say that, well, if X is only locally compact, then I can consider all those functions that vanish at infinity. What do I mean by vanishing at infinity? I mean that for every epsilon, I can find such that, but outside of this compact set, function is less than epsilon. So okay, we can take this step further. I will mention it probably later. Oh, sorry. Awesome. 3.
This is different from taking the compactly supported.
No, it's different. It's going to be complete. So compactly supported, I mean, here you're going to take functions that may live everywhere. They're not compactly supported, but they're just going to vanish. They're going to be small outside of the compactly. So 3 is the disk algebra. What is the disk algebra? There are those continuous functions on the closed unit disk. So usually by D I just mean the open unit disk and the bar over there is its closure, which are holomorphic. Holomorphic on D. Yes, and an interesting phenomenon that we're going to speak about later in the second part of the course is that, right, we can well, I need to explain what we mean by always, but let's say just for now, we can embed.
You take here the sup norm?
Sure. So yeah, so with which norm? Yes, and to explain which norm I wanted to mention something before. So yes, maybe I will mention it first. So of course we can always embed. This is a space of continuous functions on the closed unit disk. So I can think of them, although they're also holomorphic, etc. But I can think of them as a part of this example. And this example already, I mentioned that it comes with a norm, right? It's written over E. So I can take the supremum, I can take the norm coming from this example. So we can take the norm that is just the supremum. There's in fact another thing we can do. And we can also do the following trick. We can think of the disk algebra as sitting inside the continuous functions of the unit circle. How come?
Because they're holomorphic.
Because they're holomorphic. So it means that holomorphic functions, they have this maximum modulus principle, meaning it will attain the supremum anyway on the boundary, on the circle itself. So in fact, I can reduce my I don't know, something that the thing that I take a supremum on to be just the unit circle of this. It will give me the same norm because due to the maximum. Right? Because there are more. So it's the same thing. I wrote here 2 points, but it doesn't matter. With each definition you want. Usually, we will see it at the second part of the course. We will search for the smallest, for the nicest thing, right? We will want to embed this in the nicest space we can have, and this is nicest than this because it's part of it. It's smaller. Okay? So it is this guy is a kind of a boundary of this Banach algebra, but we will get it. Yes, I do want to mention this. Let's say L1 of R with a Lebesgue measure and convolution. And the norm that belongs to L1. Yeah, so by the way, I didn't mention what are the products, and now I see in one of course the product is decomposition, right? Verify. Here the product was composition, and in 2 and 3 the product was just pointwise multiplication. The question?
I have a question, Guy.
Yes, Yuri?
In the definition, we said it's a complex algebra.
Meaning over the field of complex numbers.
Right. So in example 1, X is Banach space over the complex field.
Yes.
And in 4, how do we see the complex field?
And also here, I think of continuous functions
Into
the complex.
Right.
In 4 also, these are, okay, I took them over R, but still I give them complex value.
Okay.
Okay. In fact, you can take it for L1 of any locally compact group if you want, and it will do the same.
L1.
Because I took the product to be convolution, so you want it to be closed. Okay. So okay. So definition and evolution on a complex algebra A is a map. We denote usually by star, also made to A star, such that, well, it has to be like anti-linear in fine sense. it has to be, it has to satisfy that A B star, B star A star, and that it is.
You need to conjugate.
Oh, sorry. Otherwise, this would be not good. So this is it. And sister algebra is a Banach algebra with involution such that the norm of A squared is equal to the norm of A star A. By the way, those of you who see this definition for the first time, in the first 5 minutes of today, I explained that sister algebras are a part of operator theoretical category, and right now, up until now, we don't have operators, right? We have nothing that has to do with its operators. We just have an abstract definition of the Banach algebra, which is a Banach space with multiplication, and an involution, and they satisfy some relations. So there are in fact two relations. One, a relation that sits here in calling it Banach algebra, which is the norm of AB is less than the norm of A times B. And the second relation is this one. There's also another thing which I should probably mention, and it's called the Banach star algebra. So let me mention it for a few seconds and then we will forget about it. The Banach star algebra is, so if I would give you an exercise to go on and to think about how to create a reasonable mathematical object from a Banach algebra and an involution, then it would come with a Banach star algebra. What is a Banach star algebra? It is a Banach algebra involution with involution such that what? What's the, let's say, the natural structural thing to require? What should be the relation between the involution and the norm? Without norm, yes. That's the norm of A star is A. So a priori, it seems to be very crucial or very not crucial, very natural to require something like this. To require that the involution will be isometric. And somehow it seems that Banach star algebra is more natural than a C star. So here's my first question. Is one of these guy the other? Stronger than the other? Is every Banach star algebra a C star algebra or vice versa? What?
Yeah. Second is implying the first.
If you're a Banach star algebra, you're a C star algebra. Okay. Is there anybody think something else?
It's the opposite. Huh? I think it's the opposite.
Okay. So why do you think every Banach algebra is C star algebra?
You can open the no.
Yes. So right. So what's the name?
Oh.
So O says something like I have that the square of A is A star A. Then because it is a Banach algebra, I can write here less than or equal to the norm of A star times the norm of A. Then if A is non-zero, I can erase the norm of A from both sides, I think, and then we would get, well, we will obtain that the norm of A is less than or equal to the norm of A star, right? So half of being a Banach star algebra. Okay. So we convinced ourselves that being a C-star algebra implies half of being a Banach algebra.
Can't you plug in then A star instead of A star?
But then I can plug in the A instead of A star, and but this is your direction. So this is what you said. You said that any C-star algebra is a Banach star algebra. This is correct. Okay, so let's find. I know that every C-star algebra is a Banach star algebra. Is what we just mentioned. But now think why, if the other direction is the same thing or not. I mean, if we feel the other direction. If A is zero, then this is still true. So, okay, so now A. What about the other direction? If we know that we are a Banach star algebra, can we get this identity? So this is what you, I think.
I just thought that it's equal, not small or equal.
Oh,
This is the one.
yeah. So we get half of it if we go from here to here, right? If we go from here to here, then well, if you know you have a Banach algebra, then clearly the norm of A star A is less than or equal to the norm of A star times the norm of A, which is the Banach star algebra, the norm of A. So we always have this equals this in case we start with a Banach star algebra, but not the other way around. So why not the other way around? Okay. But let's start with some examples of a system. Some examples of system, which are in particular when Banach star algebra is when. One, take H to be a Hilbert space, and take B of H to be a bounded linear operators over H with the operator norm that we mentioned before. For a general Banach space, we don't have an involution, because the dual of a Banach space need not be the Banach space itself, but for a Hilbert space, it is exactly the case. So we have the natural involution. So with the usual star. So the usual star is an involution. Think about it, and why is it a C-star algebra? So, well, we know it, right? The norm of T star T is, you can apply this right on vectors or something like this, and to see that it is the norm of T square. Do you all see? So the second example we have is taking convergence functions over X, right? these functions over X with the adjoint. So this is as before. And yes, so X is comfortable. And the adjoint is just conjugate function. So F star of X is just F of X star. And so I wonder. Okay, let me maybe mention the following thing. If X, so let's call it, we're still into the remark. If X happens to be only locally compact, Hausdorff space, that C0 of X be then algebra of all continuous functions vanishing infinity. That is, let's call it functions F. That is for every epsilon less than 0, there exists K in X compact such that F of X is less than epsilon for every X that is not K. And in fact, we can also think of this sister algebra as follows. Yes, so okay. So this is also a sister algebra with the same. And this is also a sister algebra. Same norm. But another way I want you to think about the sister algebra is as follows. So you can always consider the one-point compactification of X. So if X is non-compact, if X is compact, then this definition and the previous definitions are the same, right? This is just zero. If X is non-compact, let X union with another point called infinity be it's a one-point compactification, minimal compactification, like some compactification, whichever terminology you like. So I can always embed, I can always think of this, identify this sister algebra as a sub-sister algebra. So this is not compact, right? So I can think of C0 of X as, of course, I'm doing there some kind of isomorphism that I still didn't define. So now let's just think of it. I think of it as all the functions on C of X with infinity such that f at infinity is 0. So this is honest to God subspace or subalgebra of C of X. So to wrap it up, what I wanted to say here is that even though I discussed here only about compact Hausdorff space and continuous functions over it, even if I happen to have a locally compact Hausdorff space, I can in fact think of it as a part of this example, as a star subalgebra of this example, without defining exactly. Okay, here of course I need maybe to have a real isomorphism in the right category of sister algebra, which I didn't define yet, but right here, right now, it looks reasonable. And in general, so this was example 1, 2, 3, any subalgebra or any sister algebra, star subalgebra. Of so by star subalgebra, I mean subalgebra with a star that belongs to the big C star with the same involution. I don't take another. So this will also be a C star.
Don't it require it to be closed?
So okay, it will be automatically closed, but I agree. Let's now consider it closed. Okay. So let me call it systems. Yes, a priori you might think, okay, Guy, if you do need to close the algebra, we'll get to it. Right now, it's a special algebra, meaning a closed subalgebra with the same star and everything. And now let's see some examples that are not. So examples of Banach styles that are not this algebra. And so the one that we mentioned before, L1 of R, following star with F star of X, it's just F of minus X. Conjugate, this is not a star algebra, but it is a Banach star. Is oh, still the sheet Banach star. Can you see why this is not a sister algebra? Okay, you can construct an easy example. I would like an exercise. This to yourself. For I can you consider the disk algebra with f of z, so star will be f of c bar bar. Right? If I take here only one bar, it will not be homomorphic anymore. But if I do this, it will be homomorphic. But this is not. This is a Banach star algebra, which is again. Yes, we need to think of a
Of the more natural
function.
examples?
What?
Of the more natural examples?
Are there more natural examples for what?
Star algebra.
There are many natural examples of star algebra, not sister algebra. So in fact, here you can take this is very natural, L1 of any locally compact group, same operations. So it also not be in general. And also, if you want a not an unnatural example, you can take any Banach space. Any Banach space. With involution, you don't even need involution, you need less than that, with antilinear. Isometric map. If you take the zero product, this is of course Banach algebra. If you take this, well, it's an involution, but in fact I need to write it doesn't need to satisfy anything about the product. So I wrote here an antilinear isometric star, and then it will be of course Banach star algebra, which is not a sister algebra in general. Right, because A star A will be 0, A squared.
Yeah, we're working with the same norm.
The norm of this Banach space, we take a Banach space.
So for the two previous examples.
So the two previous examples same norm. From now on, whenever I write L1 of R or A of Z, I mean with the norms that I mentioned before, the same goes for C of X and same goes for B of H unless I state otherwise. Now I see that there is another example I want to make for sister algebra. I can make it later, but do I want to make it today? Let's make it now. So I'm done with examples of Banach star algebra that are not, and I want to give another example of sister algebras.
I can ask what the A times B is 0, it will be.
Yes, I mean, I define a product
Okay.
for all A and B. So it's
Guy, can I?
Really?
Sorry, do you hear me? I have some internet problems.
The internet problems
Okay,
are
so-
my side?
No, mine. I'm now with my phone hotspot. So we didn't require these algebras to have a unit, right?
At this point, no.
Like, okay, so also the involution.
For example, does not have a unit.
Yeah, right. And in the involution, we won't require like a unit to go to unit.
Of
If
course,
there is one.
No, of course, there is no unit. This group is not.
Yeah. Okay. Okay. Just want to make sure this.
Okay. And
If you have a unit, the unit will go to the unit under the involution, I think, automatically.
that's right. So we will discuss about it in a few minutes. I did not mention unit at this point. And I want to give another example of a non-unital, whatever that means, sister algebra. So, for example, of a C-dogma. So again, it's going to be a sub-algebra of a sister algebra. Before, it is a special case of 3. Of this. So this. K of H is the compact operators in B of H. So what is a compact operator? It is just an operator that maps, well, probably all of you guess that this is the definition, but let me remind that it is an operator that maps the closed unit ball into something that is pre-compact. That if you close it, it becomes compact. Okay, so these are all the operators, all the operators T U of H such that T of the unit ball H closure is stop. And the operations are the same operations you get in U of H. So with the norm and star from U of H. So let's think for a second why this is true. Wait, so first question, why is compact operators form an algebra? Why a composition of two compact operators with a compact operator? And so we need to check that the composition of the two compact operators to such is compact. That's easy. We need to check that it is closed, right? That's easy as well. Well, that's not really the exercise. And yes, and more complicated, or maybe equivalently complicated to two. Think about it. Why is it closed under stars? Right? It's not clear why a star of a compact operator needs to be compact too. Can you see it immediately somehow? Well, with this definition, of course. Of course, if you choose another definition, then it's okay. So think about it. If you know the answer, then great. If you don't, this is going to be also an important example. So later, so I wanted to mention it now.
Why do we need to check if it is closed?
Because it needs to be a Banach space, right? I mean, it needs to be, well, it needs to be a Banach algebra first. So it needs to be a Banach space. It needs to be closed, complete. It's closed and it's capable. Yes, before that, you probably asked me because I wrote before a star sub-algebra, and then Michael asked me if I need to require closed, and right now I wrote close. Yes. Okay. So we need to decide about the break, by the way. How do you want it? Do you want it to be like a 15-minute break after 1.5 hours, say? This makes sense? Or 1 hour and 25 minutes or something? So 2 breaks or 2 short breaks? My only problem is that, at 4:30, I need to run because I need to pick up my daughter from daycare. So I just need to run in 4:30, so I'm not able even to wait here 5 minutes. So I think
It's okay.
no, yes, I think yes, we should continue and maybe have a one break, like 15-minute break somewhere. So you can tell me
Maybe at 3.
in 3,
Oh.
and then it could be maybe 3 quarter.
3:15.
Yes, and then we'll have another. So, unit. Before unit, let me discuss about ideas. I mean, just briefly, then we'll get into a deeper discussion about ideas. But for now, the terminology by ideal of sister algebra, we mean a closed two-sided ideal. Another exercise regarding example 4 and show that if I and I will want to mention algebraic ideas, namely not necessarily closed, then I will call them algebraic ideas. Because the category, this category is algebra, usually closed ideas. And now about the unit. So and a joint so definition and the sister algebra A is unital if it has one that is an element such that 1 times A is A times 1 is A or and unit to see the unit is unique, of course. I mean, we don't need to imply it. It's just the way it is. So remarks. 1. It is unique if 1 prime is another unit. Then 1 prime is 1 prime times 1, which is 1, I guess. And 1 star is also a unit. Plus 1 star is 1. Make sense? Agree? One norm square is 1 star 1, which is 1. So is what? It's 1 for 0. So yeah, so if the norm of 1 is 0, then it means that
This is the zero algebra.
this is the 0 algebra. So let me add here a question. Is sister algebra, which contains only one element? Unita? Yeah, so there is a very famous sister algebraist, and that is it's very old now, and he's a kind of how would you call it? I think a troll. You can give like a very deep talk in conference about sister algebras, and then he raises his hand and say, "But what if this is the 0 sister algebra?" It's unital, of course. It's not unital, depending what ruins your statement. I don't know. So sometimes people just add the requirement that a unital sister algebra, that it has a unit which is not 0. Okay? Sometimes people add this requirement. But of course we don't really care about.
What's the name of the system algebra?
No.
In our fancy?
What?
What's the name?
No, I don't know what to say.
Ah,
You were meeting at a certain point. What's your guess? No, we're recorded. We can't. Okay, now, and that's the part that we want to go. We say it's non-unital. Say it's non-unital. It's algebra. Then we can define A1 or A plus or whatever, several sometimes. Like this. Then its unitization. It's fine. So, as a vector space, this is simply going to be a direct sum complex numbers, and we will write its elements as a plus number 1. And well, it's a vector space, so I need to define a addition and scalar multiplication, but there's one particular way to it. Okay, I said it. I don't need to.
Yes, you don't.
It's only the multiplication. You just remind yourself what I did. And the product. But you know how to define the product as well, right? You see? The edge of it. This gives an A plus structure of unit system evolutive algebra, complex algebra, algebra. More information, no? Because evolution, complex algebra, we need the norm, right? We need the norm. We need the norm, and then we need to verify that it's going to be system algebra. But before even having a norm, even just algebraically, know that A sits inside A plus as an ideal, algebraically speaking. Just note that A sits inside A plus. Well, I don't need to say even algebraically right now because I have no structural system.
Why do we do this construction? We try to build something unital.
Exactly. So many times there are things that are easier to say about unital system algebras, as we're going to see later on. But life are not amazing, and sometimes we bump into system algebras that are not unital, and we want to unitize them, do whatever we want to do, and then forget about the unit and go back to the non-unital thing. And this is something that we will use. And okay, so let me give you the name. I want to write algebraically, but it's stupid because there is no other interpretation. So the norm will be following. So consider well. Recall that we start with the system algebra A, right? With the non-unital system algebra A, but in particular it is a Banach space because any system algebra is also a Banach space. So think about B of A. This is a Banach algebra, right? Bounded linear operators over A. A just as a Banach space. So this is a Banach algebra. So now I can define the following thing. I can do the following trick. I can think of A plus lambda 1 as left multipliers, or has a left multiplier. By this I mean as an operator that I'm going to denote it by left L of A plus lambda 1. L sub A plus lambda 1. So this is going to be in B of A. What it does to an element B, well, it multiplies, well, it multiplies from the left. So does this make sense? But this thing, B of A, this does have norms, right? These guys do it. And that's the norm I'm going to use. So, and then I set A plus lambda 1 to be the norm of A. But does this make sense? I mean, what happens if I take somebody that was already in A, like A plus 0, 1? So is it true that the norm of L sub A is the norm of A? Because otherwise this is just to extend the structure of A into A plus. And is it true that A is the norm of LA? When I start with A, that is A. What do you think? It's called right? Check on the yes,
But you also achieve the norm of A by just divide by 1.
By A star.
That's what Weizmann says. So you're right. So half of the solution is what Aviv said, and half of it is what Itamar said. It goes like this. Think about it. On the one hand, it is a Banach algebra. So it means that if I plug here B, I will have LA acting on B, which is just AB, and will be less than or equal to the norm of A times the norm of B. So I'll get that
The norm
B
is an operator or vector?
The norm
B
of LA
is an element of A. So it is a vector in some sense because we think of A also as a Banach space. What?
What you just said means that the norm of LA is at most the norm of
Exactly. So what we just said is that the norm of LA is bounded by the norm of A, less than or equal to the norm of A, in inequality I just mentioned. Now Itamar wanted to get equality, and he said maybe you should use A star instead of B. Why? Because then somehow we will have the sister identity, which will make everything goes together, right? Equality. And I think this should work. Let's try. So let's try. So on the one hand, LAB just AB, which is less than 8x, showing that LA is less than A. On the other, this is what we said. On the other hand, other, and LA A star is A star A. Maybe it's easier to write it like this. I can consider if A is not zero, then I can consider A star over the norm of A. So this is a norm one vector, but we get here right that I can maybe scale it out, and I get here A star, which is exactly I can so this shows that LA is A. Also. So this definition does extend the norm from A, which is good. And now we need to check the sister identity. Well, we don't need to check the fact that it is a Banach algebra because we already know that this guy is a Banach algebra. So of course, these elements would form a Banach algebra too. So we just need to to check the sister identity. As B of A is a Banach algebra. A plus is a Banach algebra too. The Banach algebra too. And it remains to check. The sister identity. So the sister identity is just identity. It's just that A star A, its norm is the normal base.
No, you're embedding in B of A. One is the identity operator. Scalar one, the unit that you added. Like 0 plus lambda is just lambda times the identity operator.
Yes, you can see it from the definition. It does anything, it doesn't, it's neutral to the position of all the other registers. Okay, and sister identity. So this should be tricky. Let's try to do it. So we want to show that A plus lambda 1 norm square is equal to A plus lambda 1 star, A plus lambda 1 norm base. This by definition is the norm, is the supremum of the whole B less than 1 of A plus lambda 1 times, right? Square. But this is already an element in A, right? This is AB plus lambda B. This is in A, this is in A, this whole thing is in A. Now I can apply the sister identity from A. I can do it. I couldn't do it here because this guy is not on what I can do. So this is the supremum of what? A, B plus lambda star, A, B plus lambda. But now, this is just less than or equal to, well, that's when I was saying. That's the supremo of B, one of B star, A plus lambda 1 star, A plus lambda 1, B, which is less than. Now I'm using just the fact that B of A is a Banach algebra. And I take the big guys outside. And now I'm done at least one direction. Then let's have the 1 star. So it might look weird for a second, right? Why couldn't I start from here and then immediately from here to say something like this is less than or equal to remove the B and use the star? But you can use the sister intensity one and fixture inside of A. So now we have one side story. What about the other side? What about the other side? So yeah, so right. So if even before in the beginning we noted that if we already know that we have a Banach algebra, a Banach star algebra, then this direction is enough for being sister algebra. Because you can back like here, right? If you know that the norm of this thing star is the norm of this, then this is less than or equal to the norm of this guy times this guy, which is that again. So why is the norm of A plus lambda 1 star equal to the norm of A plus lambda 1? Just simply stop. And they can, like, with the norm of the product is less than the product of the norm, the equality of the ball. Right. So this is just H star. I mean, but in the equality right before, you have that the norm of A plus lambda 1 squared is less than or equal to what you have, and then you can take it out to the norm of A plus lambda 1. Say that this is less than or equal to the norm of A plus lambda 1 star. Yes. The norm of A plus lambda 1. Yes. And just remove the norm of A plus lambda 1 from both sides. Okay, great. This is very good. So now I can remove A plus lambda 1 from both sides and we obtain that A plus lambda 1 is less than A plus lambda 1 star. But now apply this to A star and lambda bar. Right. Lambda bar. So for inequality, And therefore, this is, we can go back and this is just an example. So, the identity. Yes. Okay. So, just to be precise, in the break, Shivik added an important comment. So, two comments. One, in the break, Shivik had an important comment. He said that I did need to say at a certain point that A plus is closed, correct? When I say here A plus is the Banach algebra 2, I needed probably to write here check it is closed. It's very easy, but still. Also, there was a certain point in the previous hour that I said something like it's enough to require that a C-star subalgebra will be star subalgebra. I didn't say that it has to be closed. Then I added the fact that it is closed, but it is important to that the C-star algebra will be closed. So everything that was written was okay. I'm just saying if maybe I said something that wasn't accurate, but I hope it's fine. Okay. Don't worry, we'll get back to the differences. Right now, I want to move here to a quick review on Banach algebras, and then to commutative Banach algebras and to Gelfand theory. But start with a review on Banach algebras. This is going to be fairly, I probably think you know. Let A, or partially know, let A be a unitary Banach algebra. And right, maybe I didn't define what a unitary Banach algebra is. I defined what a unitary sister algebra is, but define it yourself then. One, lemma if the norm of A is less than 1, then 1 minus A is invertible. And again, I assume that you know these things, so maybe we just move quickly on these. Why is this true? So the easiest way to prove it is what? Sum of A. Exactly. So, well, let me write it in one line, something like this. Show that 1 minus A inverse is the sum, so then goes from 0 to infinity. But there are things to show you formally. Right? So if you want to prove it formally, you need to define a sequence of partial sums, to show that it is a Cauchy sequence, so it converges to something, and then to show that this something has to be the inverse of 1 minus A. And this is easy. You can do it, in a few lines, but that's corollary. GLA is open. So GLA is just the set of all invertible elements. A is open. So why is this true? We can show that any invertible element, we can find a small neighborhood that will consist of invertible elements. So, okay, so let's see how do it. So let's we show that we will show that the unit ball with radius, I think 1 minus 1 over the norm of A should be enough, but maybe I'll change it in a minute. Using GLA. For every angel. Therefore, it is okay. Okay, so if I take B in the left-hand side, if B is in BA with this radius that I think should be 1 over the norm of A, then A minus B is less than 1 over the norm of A. So what? So A so A is invertible, right? I do have A inverse. What is A inverse times A minus B? This is just, so on the one hand, this is just 1 minus A minus 1B. But on the other hand, this is less than 1. Yes, it's an open. It's less than 1. So 1 minus this is invertible. So yes, and we're done, right? So 1 minus A inverse B is invertible. But this is just A inverse B. But A is invertible, so B is invertible. Definition. For every NA, the spectrum, sigma of A is all the lambdas in C such that A minus lambda 1 is not inverse. By the way, from now on, let's decide that we also write A minus lambda instead of A minus lambda 1. And theorem which I'm not going to prove, I'm just going to use from functional analysis in any line of algebra. Is open, is compact, non-empty, and non-empty. And the resolvent function, are A of lambda, which is A minus lambda inverse. And I think of it, of course, it makes no sense to apply this in spectrum. So from C minus, you see. to A, sorry, is holomorphic. Well, by holomorphic, choose one of the reasonable definitions. Choose this definition, meaning that for every functional, just functionals over A, the composition of the resolvent is phi. You can give other definitions for logical vector spaces, valued functions that we coincide with. And so definition, the spectral radius. So before I move to the definition, does everybody here know this? I mean, at least that the spectrum is non-empty and compact.
Yeah, I used to know.
You used to know it's fine. If you used to know it's fine, you can open Wikipedia or a book. Just verify that you're familiar with this. I'm not going to give the details. It's a really nice proof. I mean, it's one of the nicest proofs I think in functional analysis. Yes, okay. So definition, the spectral radius, the spectral radius of A is denoted by rho of A, and just take the supremum over all lambdas in spectrum. So you should think about it like this. Right, you have a sort of a spectrum, it's some kind of a compact set. So this. Then this radius, right? Separate this. Claim. Spectral radius is always less than or equal to the norm. Proof. If A is less than lambda, the norm of A is less than lambda, then it means that 1 over lambda times the norm of A is less than 1. So 1 minus this thing is invertible. Also, if you multiply it by lambda, lambda is non-zero because of this. So even if you multiply it by lambda, it will be lambda minus A invertible. But this means that lambda is
you don't need the number. Right?
Thank you. Lambda is not expected. So this shows.
What is it?
סוגיות. נכון. צודק. אז סוגיות באדום. כאילו איכשהו,
לא החלטתם, כאילו פשוט A, לא החלטתם תהילה.
אותו דבר.
רגע,
כן, זה אותו דבר. אבל-
לא, זה לא, אני לא יודע אם זה לא שנייה.
אם תשים אינדוס שם או תוריד אחד חלקי.
אף אחד לא אמר שנורמה של A אינברס, לא, אני חושב שמה שהשתמשתי בו, פה היה בזה. זה גם מה שהיה לי בראש פשוט, אפילו לא כתבתי. אוקיי, סליחה, זה נכון. בסדר, אתם רואים? כי כשעברתי את זה אגב פה, אז הכנסתי את A אינברס. זה לא נכון שזה שווה, כאילו, אולי כן, אבל זה נכון. עכשיו, האי שוויון הזה של הרדיוס הספקטרלי ביחס לנורמה הוא יכול להיות סטריקט. מישהו יכול לתת לי איזה דוגמה פשוטה?
What did you say about the strict?
So we may have rho of A is strictly less than the norm of A. So do you have a simple example, not something complicated for this. So we look for something that will be that we will be easily able to analyze its spectrum. I don't know, 2 by 2 matrix, let's say. Because for 1 by 1 matrix, this would fail. But for 2 by 2 matrix. For 1 by 1 matrix, we always have equalities about this. The 2 by 2 matrix makes sense.
Yes.
So, oh, are we? Glad? With the masks, I mean, even before I was not so good with names and faces, but with masks, I used to masks. Yeah, thank you. So, example, like the Jordan block, let A be 2 by 2 matrices over the complex numbers. This is how I'm going to write it, okay? Less than 2. Because we know we are over the complex numbers, always. And A be, I don't know, 0, 1, 0, 0. Of course, we can choose another Jordan block. The spectrum of A is what? 0. Is 0. Right? A is not invertible, but once you have something with diagonal that is non-zero, it becomes inverted. So the spectral radius is 0. But the norm of A is, of course, operation of actually applying the vector which is 0, 1, unit and vector, unit vector. Okay. I can give you another example if you want. So another example. Be in the back of your mind, we can consider the operator in V of L2, 0, 1 that is just, so T of F is just point X is just the integral from 0 to X of F of T. Or if you want, you can think of it as the inner product of F and the characteristic functions of the interval 0. So why is this an example exercise? Think about what's the spectrum. Okay. please remind me at 4:25, okay? You'll be out, yes. So maybe if you be at 4:15, you can still watch the. No. Oh. It's recording. No, I thought I paused it, but I didn't break. Oh, I didn't. Okay. It's good that I didn't pause it because I never remember to. Spectral radius formula. Spectral radius formula. Theorem. Rho A is just the limit of a to the norm of a to the nth root of that. Okay, and this is something also you should be familiar with from yes, I will skip it. I mean, I don't even ask you to verify that you know. And definition. Blessing. An element in a Banach algebra is normal in a Banach star algebra. No, let's finish this one. Just 1 second. So let A be a sister algebra. Plane A is normal if A star A self-adjoint if in fact I can do it in any star, but no, self-adjoint if A star is equal to A, unitary if A star A is 1, and also A star is 1. Projection if A star is A, which is A squared, positive if self-adjoint plus spectrum lines in size 0 infinity. And yes, maybe, I mean, so it can be a nice exercise to show that in side-system algebra, being, okay, so it's not always the case, but in many cases, in side-system algebras, being close, being almost one of these properties means that you are close to an element that has this property. Being close to having this property is almost as having this property. or something like that. I'll try to explain. Okay, so this is just a remark. I mean, I want to go to another direction, but let me just give a short remark, comment.
If you want us to add something to make it have this property.
So comment. I'll try to comment. It's useful to note. It's useful. Note that inside this algebra, sometimes being having almost the property or penalty implies that being close to an element having this property, truly having this property. Having useful to know that inside the system algebra, sometimes, not always, having or almost having the property, property implies being close to an element truly having this property. Yes, this is what I wanted to say. So let me give you maybe an example. I think I guess I didn't write it. Okay, for example, is almost unitary if no, it's not. Okay, I want to say something. For example, try to prove that on the epsilon there is some delta such that bye guys for every A with A star A minus 1 less than delta and A star minus 1 less than delta. So for every epsilon there is delta such that for every A that is almost up to delta the unitary, then this implies that there exists a unitary A U such that A minus U is less than epsilon. These are very cool properties that you have in that you sometimes have in sister algebras, where you say, okay, I have some element and I don't know that it's almost unitary. Then I say that okay, it's closed. It has to be really, really close to something that is it. And
Also for von Neumann algebras, it's true, but for also other algebras?
no,
Huh?
no.
No what? Sorry.
For operator algebra, you're asking for things that are not sister algebras, that are
No,
general.
for sister algebras that are not von Neumann, for example. Like when you don't have product
It's
composition.
true. Try to prove that for sister algebras.
All sister algebras.
For what?
For all sister algebras?
Yeah. Yes. Now I have to say I'm worried that the question comes from you because I don't know a lot about these things that are now. Yes, I think I yes, I know how to prove this, but maybe I will give it as an official exercise. And I think this should work also with some of the other properties I mentioned there, but not with all of them. So a nice exercise would be to, I mean, it will require some time, but it will be to rephrase the right statement you should prove or disprove for any of these properties and check if they're true or not true in the system. But this is maybe too difficult like this. Maybe I will construct a formal exercise out of this idea. You think maybe it might be nice. Okay. But right now you can think about this. Okay. Anyway, what I wanted to say, because we're speaking about the spectral radius, right, is that so playing if so this was a bit out of context, but it's very interesting, and maybe we will get back to it later. A claim, if A is normal, then well, what I said before, the rho of A is not just less than or equal to the norm of A, but is equal to the norm of A. This can be easily seen again in a sister algebra. In a sister algebra. Yes, maybe it wasn't clear. Let A be sister algebra. B, A, sister algebra. A, let A be normal. B, normal. Then I will pay the normal A. So idea how to prove it?
We need to use the theorem from before, right?
Right? So how? And the fact that it is a sister algebra. So you know that A square norm is right? A square star, A square df. But this is just because A is normal. This is just A star A star A star A. Yeah. Right, because I can play with the order of things. So but this is just the norm of A star A. Yeah, so these are due to the sister identity. This and that. And this is those are the sister identity. That's very cool that we can take powers out of the norm. Right? So now we're almost done with this. So, okay, we can pass to the subsequence powers of a to the 2 to the n is the norm of a to the 2 to the n. So, by the theorem of a, which is the limit, well, it could be also a limit of something. Yes. Okay, for the last thing we're going to do today, okay, let's see. So spectral mapping property. And now I don't need it to be a system algebra, just a complex unit of algebra. Well, when I defined spectrum, what was my, I said the Banach algebra, right? Okay. Sorry. Let's go. But in fact, I can more general. More? So claim for every polynomial P and an element NA, and we have that the spectrum of P of A is P of the spectrum. So you can polynomials and taking spectrum, something that can be. Okay, so let's see why this is true. Oof. If P is just a constant polynomial, then we're done. We are done. Great. Spectrum of constant is constant. Otherwise, right. Or otherwise, for any lambda in C, decompose your polynomial as so no, I don't want you to decompose P of Z, I want you to decompose P of Z minus lambda. So this would be some kind of alpha times Z minus beta I goes from 1 to n. Oh, let me even okay. So alpha is 0. Now, since the so I plug in A, so since the A minus beta I commute with each other, and right, because they are all just A minus something, PA minus lambda is invertible if and only if all the A minus beta ions and therefore if I take a lambda from the spectrum P of A, this is equivalent to say that P of A minus lambda is an invertible, which is equivalent to say that there exists an I such that A minus beta I is non-invertible. So there exists a zero of the polynomial. So there exists zero of the polynomial. So just the zeros of the polynomial such that this is not in the spectrum wait. It is. This is not one. But this is just another way to say that there is somebody in the spectrum of A. Something over something. Or in other words, lambda. Something is lambda. Sorry, lambda. So in other words, lambda in the polynomials. Yes. Okay. Okay. Lemma. In any, again, this is true for any complex algebra, let me say in Galvanic algebra. The spectrum of AB is equal to the spectrum of BA. There's something weird here. This is true up to, I think, the origin. Why? So, right, for lambda non-zero, we need to show, we need to show that is correct, that lambda is in the spectrum of AB, if and only if lambda is in the spectrum of BA. But we can, right, since we can always replace AB by AB over lambda or things like that, then it's enough to do it for one. So enough to check that one is in the spectrum of AB if and only if one is in the spectrum of BA, but this is just to say that so it is enough to check. So enough to check that 1 minus AB is invertible if and only if 1 minus BA is invertible. So why is this true? So I'm going to do the same trick from before with 1 minus A. Remember that 1 minus A, that if the norm of A was less than 1, then 1 minus A is invertible. You choose the guy that needs to be the inverse. So let's assume that this guy is invertible. Who should be the inverse of this guy? Well, the inverse of this guy, if it exists, it should be the sum of AB to the n goes from 0 to infinity. So yes, it's like a Twitter comments. Non-official proof. Non-official proof. We do something like this. We say that 1 minus AB inverse should be n goes from 0 to infinity AB to the n. But now I can write this like this. This is 1 plus n goes from 1 to infinity AB to n, right? And now we can take A outside and B outside, but in the middle we will have BA. You see it? So this is 1 plus take A outside, take B outside, and in the middle you will have n goes from 0 to infinity BA to the n. But this guy must be the inverse of this because I assume that this is invertible, and of course if this is invertible, this has to be the inverse. Again, from the same reason that I mentioned before. You need to verify that this converges to something, and then it's easy to show that this has to be the inverse of this guy. So this is 1 plus A times the inverse of 1 minus BA times B. Now this was the unofficial proof. So, but now that you know that this needs to be equal to that guy, you can simply multiply them both. So you can forget about the sketch. Simply say if this is invertible, this is the inverse. I will check that this guy, when I multiply it with 1 minus AB, then I get 1. Then you can check it and it works. Now check. Now just check. Just check that 1 minus AB. I know that we are out of time. Just one thing. And I will not have time for questions, so sorry for that. Next time you need to remember to leave some time. Okay. So just finish this quick example. Let S be bounded L2n. One operator of L2n, being the shift. So S of A0, A1, etc. is A1, A2, etc. Check what are the spectrum of S star and spectrum of S star S. And you will see that they are the same, but not exactly the same. You need to have the zeros. Quick question? Okay, great. So I have to leave.
Next time, 15 minutes earlier.
Next time we decided 15 minutes earlier. Yes. I will remind you in a mail, I guess. I hope. Yes. Okay. Bye.